All right, I'm going to record a quick demo video here on how to do processing for the GeoSun data. This is a data set that I collected. When you download data from the LIDAR, these are the files that you get, the folders you get. I also collected data. I set up a GPS base station and I converted it to Rhinex and I uploaded it to Opus. For technical reasons, I set the antenna height to 0 and I say that there's no antenna. So this way I get a position at the antenna phase center. This is just a way of, roundabout way of getting the exact coordinate of the phase center, and then I don't have to worry about antenna heights or anything. If I go back here, this is the Opus solution. These are the coordinates in NAD83. So let me open up, this is the gAirHawk software. And if I say File, New, it's a cemetery. The software reads the contents of these directories. You can see it's already modifying them. The rover data, LiDAR files, photography files. And then we just have to put in the input coordinates. So for this, I'm going to use the X, Y, and Z in Ohio South, X, Y, and Z. These are Earth-centered, Earth-fixed grid coordinates. Okay, it converts that to a latitude and longitude in decimal degrees. You can see over here that the ellipsoid height that it computes is exactly right, 25.862. Or 255.862. I'm going to actually change that to orthometric height because I don't want an ellipsoid height point cloud. And then, as I said, I can input in the antenna height and the distance to phase center if I know the antenna model. That's more complicated than what I think is needed. That's why I just, when I uploaded the base data to Opus, I just said that there was no antenna and it gave me a phase center. I can explain that more if you have questions. So I hit OK, it loads the data, and then I can specify when the LiDAR is flying. I'll show you here, there is this, so straight up from the LiDAR system is 0, then there's 90 degrees and 180 is down. So when the drone is flying, you want a swath width that covers about 90 degrees. So from about 135 to I think 225 is the magic number there. You could process the whole data. You're going to get stuff up in the air though, maybe birds, that type of stuff. So I always just set this to 135 by 225. Range 5 to 60 meters. You don't want stuff close to you, too close to you. Then we set the coordinate system to Ohio South for output. Then we do the strip adjustment here. So it's reading the base file in the drone rover file and produces this. We have to do a manual strip. So we just say, okay, we flew from here to here, here to here, just specifying the strips of the flight. There is some automated methods here, but you don't want, with LiDAR systems like this, with one antenna, you don't want to collect and use the data from when the drone slows down and makes that turn. That's where the most errors are going to occur in that IMU. When it's moving straight and slowly across the site, that's good data. But these short turns and tight segments, try to get rid of that data. So we're going to hit apply. And for this data, we want to do a strip adjustment. We're going to optimize the point cloud, and we're also going to colorize it. Hit start calc. This is going to take a few minutes to run. I will pause this video and be right back. Okay, so that is finishing up in the background there, still optimizing. In the meantime, I opened up TBC. While I was out there, I shot some photo control points. My base is set to the same coordinate as my antenna phase center here. So my 6,000 points are my bases, or my GCPs. So I got 5 of them here. I will export these out. In this directory, point northing easting elevation. All right, in the background that finished. So let's bring it in and look at it. So I've got a new TBC project, or global mapper project here. My results.out, bring those in. Oops, this is in state plane, Ohio South, meters across the board, hit OK. Meters. I can look at it by color. I'm going to increase the size of these, make it look thicker. And then I will bring in my control. YXVD, yes. You can see now if I go to color by intensity, this is one thing I've noticed, that the colors aren't always perfect. I've mentioned it to GeoSun and they are working on it, but if I go to intensity, oops, and configure, turn this background black here so it really stands out. Okay, so you can see there's an X there. Let me change this one more time. Atlas shader. Does that make it better? No, it really doesn't. So there's, I know it's hard to see, but there is an X there, and that target is, that X is pretty, or that point is pretty close to the center. Make that bigger. That goes to 6. So if I zoom out, you can see there's an X there. My target's pretty close to the center. Let's measure it. Down here in the lower left, you can see it's about 3/10. So horizontally, it's pretty darn close. I have another one under here that's, again, pretty close. Let's check my ground control. One of them seems to be off. Let me see what's going on there. Oh yeah, this one was underneath the tree, and there were tombstones there. But the rest of them, you can see it's somewhere between 1/10 and 2/10. So what I typically do in this case is I will fine tune that out, and I believe it tends to be right around 5 centimeters. Let me verify that. So 0.098 plus 0.156 plus 0.167 plus 0.229 divided by 4.1625 feet. So 1/10. But what I'm going to do then is adjust this so you can see the LIDAR elevation is, let's see, one of them's in meters and the other one's in feet, which isn't helpful. But if I zoom in on this guy here, for example, and I mouse over, so this ground control point's at 946.96. This is at 946.88, so again about a tenth. 88. So the LIDAR is lower than the ground control by that 0.164. So I can, let me close this. I can alter the elevations by 0.164 feet. And now if I run that control, suddenly we have accuracies that are in the tenths of a foot or hundredths of a foot. So from here I would run a automate ground classification. So what you can see, I've got this was probably a 20-minute flight. It's taken me about that much time in the office to process it, including downloading, uploading to cores, Europus, and then bringing in ground control. So it's kind of a one-to-one, but the flight, I'll measure and see how big of an area this was, but good results. Doesn't take that. I mean, once you learn it, there's not much to it, to processing the data and getting good results. So I'll just let this finish here real quick. I'll be right back. Let this finish. While that's still running in the background, let me open a new window. Come on, Global Mapper can do it. This is all running on a laptop, so it's not record fast, but so I'm just bringing this data back in again. I want to look at it from colorization. Let's see though, I wanted to measure the acreage on it. So across the bottom, the enclosed area, it's in square meters. Sorry, let's see this, units, acres. So that's about 12 acres. 12-acre site. We flew in about 20 minutes, processed the data in 20 minutes. Now I've got by classification. If I look at it in 3D, see there's a lot of tombstones out there that may or not, that global mapper algorithm isn't perfect. You have to look out for things, but it's separated the power lines from the trees and the ground pretty well. From here I do a create an elevation grid. Thinning will go 1 meter, the lowest value. Filter using only the ground. And then generate contours. One foot, 1 meter. Let's make that 2 meters. So, it's not hard. It's really not. If I go back to this and I colorize by RGB, I make it so that it's more like a photo. you know, this all makes sense. The road is lower, it dips down, this hill slopes down this way. If I look at this from a 3D view, now colorized. There are some points that are white. This is where the LIDAR range, because it's scanning in a full 360, it's reaching out further than what the camera does, because the camera, I believe, it has a 90-degree field of view. So, yeah, that's it. Hope that helps.